Hi, so in this video, I'm going to review the thermodynamics unit for the AP Chemistry exam. Here I have outlined the order in which I'm going to teach each topic. First, we're going to learn energy, enthalpy, and how to recognize and describe energy changes in a system, where the system is the portion we single out for study, and the surroundings is everything else. Then we're going to cover the first law of thermodynamics and calorimetry, and then we're going to learn about enthalpy of phase changes, enthalpy of reaction, and 3 methods of finding enthalpy of reaction. This order is slightly different from that used in the textbook and the course description guide because I designed it so that the concepts would connect to each other a little bit better. This video will include concept review and practice problems, but the practice problems I do are not from past AP exams. Instead, they teach the basic approach to take for different calculations that you might actually encounter on the exam. For more advanced examples of AP FRQs, I have made a playlist of worked out thermodynamics FRQs on YouTube. So thermodynamics is the study of energy and its transformations. But in order to understand that definition, we need to know what energy itself is. So energy is defined as the ability to do work or transfer heat. And its equation is E energy is equal to Q plus W, where Q is equal to the energy used to increase the temperature of an object, and W, work, is equal to energy used to cause an object to move against a force. Fortunately for us, in thermodynamics, most of the processes we deal with do not have any significant work involved. So, generally speaking, we end up with this equation, that E is equal to Q. And the fact that work is almost always equal to 0 or work is negligible simplifies a lot of our calculations throughout the chapter. So now that we've defined energy in general, we can move into talking about a more specific type of energy that is relevant to thermodynamics, and that is internal energy, E. And internal energy is equal to the sum of all the kinetic and potential energies in a system. And so, since we know that E, energy, is equal to Q plus W, we can conclude that we can change the internal energy of a system by changing Q or W. But before we do any calculations with this equation, we need to understand the sign conventions associated with Q and W so that we know what sign a certain change or situation would be associated with and know if it adds energy or decreases the energy. So when Q is positive, that means the system is gaining heat, which makes sense because as Q increases, energy should also increase. And when Q is negative, the system loses heat. Now, the one for work is a little bit less intuitive, but if, say, we compress a piston, the piston that I was talking about at the beginning, then the surroundings are doing work on the system and giving new energy to it because as the gas compresses, it starts moving around faster and its temperature increases according to all the gas laws. So work is positive when the surroundings do work on the system. And the opposite of that would be work is negative when the system does work on its surroundings. And the last one is pretty obvious, but delta E, or change in internal energy, is positive when there's a net gain in energy by the system and negative when there's a net loss in energy by the system. So one last term I want to define before I get into specific topics in thermodynamics is enthalpy. Enthalpy is defined as the total heat content of a system, and its equation is H, enthalpy, is equal to E, internal energy, plus the product of pressure and volume. And enthalpy will turn out to be a lot more useful than internal energy in calculations in thermodynamics in general. But for our purposes, internal energy is generally very, very close to enthalpy in value. And why is that? Well, if you look here at this equation thing that I have E is equal to Q plus W, and H is equal to E plus PV. And so I said that work, most of the process we do with in this chapter don't really involve a lot of work, so we can kind of ignore that in that equation. And it turns out that most of the process we do in thermodynamics also don't involve a lot of change in pressure or volume. So if we simplify that and we look at these pieces, then we get H is equal to E is equal to Q. And so since enthalpy is generally more useful than internal energy, the fact that H is equal to Q in most situations in thermodynamics will turn out to be super, super useful. So now that we have the basic terms involved in thermodynamics defined, we can move into talking about one of the major concepts of this unit, which is the first law of thermodynamics. This law is the same as the law of conservation of energy, which states that energy can neither be created nor destroyed. So a good example of this in thermodynamics is what happens if you leave a glass of ice water out in a room for a couple hours. So if I leave my glass of ice water out and I just let it sit, over time, heat from the surroundings, which are at a higher temperature than the water, will enter the water and eventually cause its temperature to rise and the ice to melt. But even though the surroundings has lost heat to the water still contains all of that heat that the surroundings lost. So even though energy has been transferred around, the Q lost by the surroundings, so it's negative, is equal to the Q heat gained by the water. So if we generalize that statement, we end up with negative Q of the surroundings is equal to positive Q of the system. And in this scenario, the water is the system. So one value that we pay a lot of attention to in thermodynamics is delta E, or the change in internal energy. And the equation for that is right here. Delta E is equal to E final minus E initial. And so it's the change in energy. And so the delta E value tells us if a process is endothermic or exothermic, because it tells us in what direction and in what magnitude the change in energy experienced is. So, for example, if delta E is less than 0, then that means that the final state of the system has less energy than its initial state, which means that it would be exothermic because energy must have been released. And the opposite of that would be if delta E is greater than 0, in which case the final energy content of the system is greater than the initial, so it must have absorbed energy, which would make it endothermic. So this is pretty intuitive and we're pretty familiar with this concept, but how can we visualize this a little bit better? So one good way to do so is energy diagrams. So right here I have two templates for an energy diagram that are paired with some reactions. So looking at these reactions, it's pretty easy to tell which state, final or initial, is going to have the higher energy content. So we know that gases always have more energy than their liquid counterparts. So we put H2O in the gas form on top and then H2O in the liquid form on the bottom. And so then we look at this and we say that we have the initial state is down here and our final state is down here, and we look up here and we see that if the delta E is greater than 0, that means that our final amount of energy is greater than our initial, so that would make this equation, or this reaction, endothermic, because delta E is greater than 0, so this is endothermic, which we know about phase changes already. And it's the opposite for this one. So our H2O gas goes on top, and our H2O liquid form goes on bottom. So we have our initial here and our final here. And that means that our initial state has more energy than our final, so it must be exothermic because delta E is less than 0. So the change in internal energy is an important value that we pay attention to in thermodynamics, but it also relates very closely to the first law of thermodynamics. So the first law states that the energy content of the universe is constant because energy can neither be created nor destroyed. So whenever the internal energy of a system decreases or increases, that means that the surroundings, the energy of the surroundings has to increase or decrease accordingly. So from that, we can draw the conclusion that Q of the system, heat of the system, is equal to the negative of Q of the surroundings. Because if the surroundings, like that glass of ice water, gains some energy to melt the ice, then the surroundings has to lose that same amount. So I want to circle back to that example of the ice water melting that I gave when I was talking about the first law. So as the water sat out, energy from the surroundings entered the water to melt the ice and raise its temperature until the temperature of the water equaled the temperature of the air. So this example with the water cup and the ice melting is an example of heat flow and thermal equilibrium. So there are two important things to know about heat flow, and that's that when two objects of different temperatures are in contact, the warmer one transfers heat to the cooler one. That's pretty obvious. I think we could all know that. But something a little bit more obscure, but still makes a lot of sense, is thermal equilibrium. And thermal equilibrium is reached, and always systems in contact approach this, and it's reached when the two objects in contact are at the same temperature. So that's why after a couple hours of leaving it out, the water finally reached room temperature, but it doesn't keep on taking energy out of the surroundings and out of the environment until it starts boiling. No, it stops heating up when it reaches room temperature, and that's called thermal equilibrium. So we know that energy was transferred from the air in the room to the water, and that the first law states that the energy lost by the air in the room equals the energy gained by the water. That's what we've learned so far. But what if I wanted to know exactly how much heat was transferred from the air in the room to the water? So we couldn't do this just from the information we know so far. We would need something called calorimetry, which is the measurement of heat flow. And below I have a diagram of a typical calorimetry experiment, which involves putting an object of known specific heat in contact with an object of unknown specific heat and using the delta T values to calculate Q and specific heat. So here I have a metal that's at a higher temperature than the water, and then I place the metal inside of the water, and the heat from the metal transfers into the water until they reach the same temperature, or thermal equilibrium. So the equation that we would use to calculate our Q values, or the specific heat of the metal, is this one. Q is equal to mc sub s times delta T. So mass, m is equal to mass, c sub s is equal to specific heat capacity, and delta T is equal to change in temperature. So we're familiar with this one, but what is specific heat capacity? Specific heat capacity, CS, is equal to the heat required to raise the temperature of 1 gram of a substance by 1 degree Kelvin or 1 degree Celsius, because they're on the same scale, and its units are joules per gram per Kelvin. So specific heat capacity has a really big impact on how much a given amount of heat will increase the temperature of an object. And one really common and recognizable example of this is if you're heating something on the stove in a pan. So let's say I needed to move the pan around or touch the pan in any way. Would I grab the sides of the pan and just shake the pot from that area, or would I grab the rubber handle of the pot? Well, obviously I would grab the rubber handle because the metal of the pan is going to burn my hand. And the reason that these two can be at such completely different temperatures is that rubber has a higher specific heat capacity than does metal, which means that it takes more heat to increase the temperature of this rubber handle here than it does to increase the temperature of the metal. Okay, so here I have a really simple specific heat problem that just involves plugging in values to a formula. But I'm going to skip this one because it's pretty simple. And instead, I'm going to do a more complicated calorimetry problem that you're more likely to see on the AP. But I'll send you guys these notes that you can look at this one if you want to see how I did it. But here's a calorimetry problem. So a 70-gram piece of metal at 180 degrees Celsius is placed in a bucket containing 400 grams of water, whose specific heat is 4.184, at 25 degrees Celsius. The final temperature of the mixture is 28 degrees Celsius. What is the specific heat capacity of the metal? Assume no heat is lost to the surroundings. So before we do any calculations or try and set up any equations, we should assess which variables we already have. So we have the mass of the metal, the initial temperature of the metal, the final temperature of the metal, and then for the water, we have its specific heat, its initial temperature, and its final temperature. Oh, and its mass. So we can go ahead and set up our equation for calorimetry, which is Q is equal to mc sub s delta T. And we can notice that we have all the variables that we need to calculate Q water, or the heat change experienced by the water. So we could go ahead and plug those in. So when we multiply that out, we end up with 5,020.8 joules. And that's the heat change experienced by the water, but what does that tell us about the heat change experienced by the metal? So if we remember the first law, and if we look at this statement right here, assume no heat is lost to the surroundings, then that means that the energy content of the system, the water and the metal, is constant. So if the water loses or gains heat, as it does with a positive Q value, then that means that the metal has to lose that same amount. So Q water is equal to negative Q metal. So now we can go ahead and plug in our values to this equation, but for metal. So Q metal is equal to mc sub s delta T. We could solve in terms of specific heat. And our Q is going to be negative 5,020.8 because it has to be the opposite or the negative of the water value. And then we just plug in the rest. So when we multiply all of that out, we get 472 joules per gram degree Celsius, and that is the specific heat of the metal. So I mentioned earlier at the beginning of the video that enthalpy is a really important concept when talking about thermodynamics, and that it actually turns out to be more useful than internal energy in doing calculations and making assessments of different things. So basically the rest of this video is going to be involving finding enthalpy in different scenarios and how we can use it to draw conclusions about different processes. So the first and probably the simplest application of enthalpy is the molar enthalpy of phase changes. So right here, I have a diagram of the different phase changes that a substance can undergo. And the green arrows indicate that you're going up, and you're going from liquid to gas, solid to liquid, solid to gas, even. And we know that the final state of all of those is going to have a higher energy than the initial state, which means it must be endothermic. And it's the opposite for the red arrows. You're going from gas to liquid, liquid to solid, gas to solid. The initial state has a higher energy content than the final state, so it must be exothermic. Energy is being released. So we already know the direction of the enthalpy change associated with each phase change. But what if we wanted to quantify it? If we wanted to know the actual amount of energy that is required to go from those stages. So to do so, we use molar enthalpy of phase changes, which is defined as the heat absorbed / released as 1 mole of a substance undergoes a given phase change, and it's in units of joules per mole. Okay, so one important application of the molar enthalpy of phase change is heating curves, and using heating curves to find out how much heat is required for a given transition or temperature change of a substance. So here I have an example problem, and it's asking how much energy is required to completely vaporize 200 grams of negative 3 degrees Celsius ice. So they gave us a heating curve, and they gave us all 3 specific heats for water because specific heat depends on temperature, and then they gave us 2 molar enthalpies of phase change, heat of vaporization and heat of fusion. So we can assume we're going to be using some different values here. So before we start any calculations, let's take a look at this graph. So we have a sort of unusual graph, and we have 2 types of regions. So we have the sloped regions, and we have these flat portions. And so if you think about it, you probably would imagine that the graph of water being heated up would just be a straight line graph like that. But actually the temperature increases in steps like this. So we need to figure out what's going on during each of these steps. So when the water is below its melting point, it's ice, and its temperature is increasing. So it's just heating up within a specific phase. So we don't have any changes to the specific heat of it. So we can actually just use this equation from calorimetry. But on the flat portions of the graph, those are during phase transitions. And since specific heat depends on on the phase of a substance, we can't really use specific heat when we're dealing with a phase transition and you're kind of between them. So the equation we use for that is delta H of the phase change times moles of the substance. And a quick explanation of why these areas of the phase changes are flat is because when a substance reaches its boiling or melting point, all the heat energy is used for the phase change. So that means that temperature remains constant. Hence, those parts of the graph are flat. So we can move into calculations here, and I've broken up this problem into 5 steps. So the first 4 steps are just basically the steps on the graph minus this gas one, because we can stop our calculation once it's vaporized, so after the boiling point. So the first step is ice going from -3 degrees to 0 degrees Celsius. So we can see on the graph that that is a sloped portion, and we know that it's still all within one phase in this part of the graph. So we can use Q is equal to C sub S delta T. And we can go ahead and plug in our values for that. Okay, so I went ahead and did the calculation because we already learned how to use this equation. But one thing I just want y'all to notice really fast is that I use the specific heat for solid water or ice, not for liquid water, the 4.184, which is the one you're probably more familiar with. So now we can move into the next step, and this is our first phase transition. So we need to use our delta H times the moles. And our phase change that we're actually dealing with is fusion or melting. So we can just go ahead and do that. So in order to do this calculation, we need to know how many moles of water we're dealing with. So we can go ahead and calculate that. And we all know how to do molar mass and find moles from a given amount of grams, so I'm just going to skip this part. Okay, so now I've found my number of moles, which is 11.1017. So I can go ahead and multiply that by the heat of fusion, 6.01, which is given, times our moles, 11.1017. And when I multiply that out, I get 66.72. So the next 2 steps are liquid water heating from 0 degrees Celsius to 100 degrees Celsius, and then liquid converting to gas. And both of these steps follow the exact same procedure as the ones that were similar to them before. So for step 3, I'm going to follow the same procedure as I did for 1, only that time for step 3 I'm using the specific heat of liquid water. And then for step 4, I use the heat of vaporization, but I follow the same procedure as I did for step 2. So I'm just going to go ahead and skip those, and then I'll show you how to do the last step. Okay, so I went ahead and I finished the last 2 steps, and I have done all but the final step. But before I do that final one, I want to point out the huge difference between this amount of energy that it takes to convert ice to liquid water and this amount of energy that it takes to convert liquid water into water vapor. So the big difference between these two can be ascribed to the difference between the intermolecular forces between a solid and a liquid and a gas. So when a substance converts from a solid to a liquid, its molecules are still relatively close together in the liquid form. So you're not completely breaking those IMFs up. You're just giving it enough energy to resist them somewhat. But when you convert a substance from a liquid to a gas, you're basically severing all of the intermolecular forces between the molecules. So it requires a lot more energy. And that's why those are so far apart. And then for the final step to get the answer to this question, all we have to do is sum the energies, which I've already done. I just add together all 4 energy values that I got for each of the steps. So this one, this one, this one, and this one, and that gives us 854.53 kilojoules. Okay, so now that we've discussed molar enthalpy of phase changes, I want to move into discussing enthalpy as it relates to reactions. So here I have 2 GIFs of an exothermic reaction where energy is being released and an endothermic reaction where energy is being absorbed. So we already know the direction of the energy change because we know what happens in an exothermic reaction and an endothermic reaction. But what if we wanted to know the magnitude? Well, in order to find the magnitude of the energy change or the change in heat content, we would need to know something called enthalpy of reaction. And here is the equation for enthalpy of reaction. Delta H of reaction is equal to enthalpy of the products minus enthalpy of the reactants, and it's given in units of kilojoules per mole reaction. So enthalpy of reaction is a really useful value that tells us a lot of things about a reaction. So first of all, it tells us whether a reaction is endothermic or exothermic, in much the same way that delta E tells us if a reaction is endothermic or exothermic. But a little bit less obvious is that it tells us the delta H of its reverse reaction. So here I have an example to demonstrate that. So here is my forward reaction. And we can see that the products have a higher energy content than the reactants, so delta H is greater than 0. And here is my reverse reaction. It's the same reaction, just in the opposite direction. And so we can see that my delta H is actually less than 0 now because the products have a lower energy content than the reactants. But since delta H is just equal to the difference between the enthalpy content of the reactants and the products, delta H of the forward reaction is equal in magnitude to delta H of the reverse reaction. The only thing that's different is their sign. So this observation gives rise to this conclusion about delta H of the forward and the reverse reaction. Delta H of the forward reaction is equal to negative delta H of the reverse reaction. And this piece of information is really helpful in our later calculations. And just one last note before I move on to more applications of this enthalpy of reaction concept, it's that delta H of the reaction depends on the state of the substances involved in a reaction equation. So one way to visualize enthalpy of reaction or enthalpy changes in general is by an enthalpy diagram. And so here I have an example of one, and I didn't show you guys how to do it because it's exactly the same as the way you do energy diagrams. So the final state has a higher energy level, so it goes on the top, and the initial has a lower, so it goes on the bottom, and that would make this reaction endothermic. But before I move on, I want to point something out about the way I wrote the reaction here. So there's two ways to write enthalpy of reaction with a chemical equation, and that those two together, the balanced chemical equation and the enthalpy of reaction, are called a thermochemical equation. And so the first way is the more common way, which is just to write it out right on the side here. But you can also write it into the equation itself, like in this second way. And so because it's endothermic and you put energy in so that the products have a higher energy content, the heat of reaction is on the reactant side. But if it was exothermic, then heat's being released. And so heat is treated as a product and it would go on the product side. So heat of reaction gives us how much energy is absorbed or released when 1 mole of reaction is carried out. But generally speaking, we don't do reactions in specific molar quantities, and we have some random number of moles. So we need to be able to figure out the heat change experienced in a reaction, Q, by using delta H. So we can go ahead and do this with this problem, which is asking how much energy is released when 224.8 grams of nitrogen gas reacts with excess hydrogen gas to form NH3. So we know that this reaction is exothermic because it's saying energy is released and because we have a negative delta H value. And so all it takes to figure out how much energy is released is to set up a quick stoichiometric calculation. So we're looking for kilojoules. So we put that on the equal sign, and now we just plug in what we know. So we have 224.8 grams of nitrogen, and then the molar mass of nitrogen is 28 grams of nitrogen per 1 mole nitrogen. And then we can plug in our delta H, so 1 mole reaction is per negative 91.8 kilojoules. And so so these two cancel, but it seems at first glance like these wouldn't cancel because it's moles of nitrogen and moles reaction. But if we go up to the equation here, we notice that the coefficient on nitrogen is in fact 1. So 1 mole of nitrogen is also the same for our purposes as 1 mole of reaction. So we can cancel those and we just get kilojoules. And when we multiply that out, we get negative 729 kilojoules. So we know how to handle delta H and how to use it to find the amount of heat Q that's required for a specific amount of reaction. But all of this depends on delta H being given to us. So how can we find it if it isn't given? Well, it turns out that there are 3 methods for finding delta H that we cover in this chapter, and they are bond enthalpies, heat of formation, and Hess's law. So we can go ahead and start with method 1, which is bond enthalpies. So bond enthalpy is the energy required to break a bond or released in forming a bond. So remember that when you break a bond, you have to put energy in, and when you form a bond, energy is actually released. That's just a general rule that's pretty important to this equation. So delta H of the reaction, or enthalpy of the reaction, is equal to the sum of all of the change in enthalpies for the bonds broken minus the sum of all the change in enthalpies for the bonds formed. So the reason that these terms have the sign that they do has to do with the energy change associated with breaking a bond. You have to put E in to break a bond, so it's positive. And energy is released when you form one, so it's negative. So here's an example of using bond enthalpies to find the heat of reaction. So find delta H, the enthalpy of reaction, for CH4 plus 2O2 reacts to form carbon dioxide and 2 waters. So the first step for any of these bond enthalpy problems is to draw the Lewis structures for each of the products and each of the reactants. And after doing so, we can count the number of each type of bond broken or formed in the reaction. So I've gone ahead and I've drawn the Lewis structures for each of the products and each of the reactants of this reaction. And I've color-coded in different colors each type of bond. And so if I were to count these up, I would get, for each of them, I'd get 4 CH bonds, 2 double bonded oxygens, 2 double bonded COs, and 4 single bonded OHs. And so we can go ahead and plug these into our formula, but just really quickly, we want to make sure that we delineate between bonds formed which are the bonds of the products, and bonds broken, which are the bonds of the reactants. Okay, so now that we know how many of each type of bond we're dealing with, we can go ahead and just plug in known bond enthalpies for each type of bond into our equation to get the final heat of reaction. So here I have a table of the average bond enthalpies of a lot of common bonds we see in chemistry. And I've gone ahead and I've highlighted in the corresponding color the bond enthalpy of each of the bonds we're using in this problem. So we can just go ahead and start out our equation. So we start with 4 CH bonds and we multiply that by its average bond enthalpy, so 413. And then we add to that, and remember we start with the reactants because those are the bonds broken, so that's energy in. So 2 times 495, because we have 2 double bonded oxygens, and those are the bonds for the reactants. And then we just go ahead and subtract the bonds for the products. And when we add all of that together, we end up with negative 808 kilojoules per mole, and that is the heat of reaction calculated using bond enthalpies. So another way to find enthalpy of reaction is by using enthalpy of formation. And standard enthalpy of formation is defined as the change in enthalpy that occurs during the formation of 1 mole of a substance from its constituent elements in their standard states. And that little standard state thing means the state that it's in at STP, essentially. So oxygen would be a gas at STP. So the equation for finding heat of reaction from enthalpy of formation is heat of reaction is equal to N sigma delta H heat of formation for the products minus N sigma of the heat of formation for the reactants. So this is just the coefficient. The N is the coefficient attached to each substance. So if you had 2 O2s in your equation, you'd have 2 attached to that heat of formation for oxygen. And so why are these positive and negative? Well, you're actually forming the products. So that's why it'd be positive, because it's just the heat of formation. That's what's happening. But this is negative because remember, delta H of the forward is equal to negative delta H of the reverse. And since the reactants are being broken down, well, the reactants, that's the reverse reaction of forming them, so you actually get the negative of its heat of formation. And a quick note, just for calculations, is that the heat of formation for an element in its standard state is 0. So an example would be EX delta H of O2 gas is equal to 0. And that's just something to keep in mind for this problem. So here's an example of finding the heat of reaction from heat of formation. So we can go ahead and set up our equation for the heat of the reaction. So delta H is equal of reaction is equal to 2, that's your N, is equal to 2 times the heat of formation for NO2, because your coefficient on NO2 is 2, minus, I'm going to put it in brackets, 2 times the heat of formation for NO plus heat of formation for O2. And we can go ahead and cancel this O2 out because we know it's in its standard state, oxygen gas. So the heat of formation for that is going to be 0. So we can go ahead and plug in our known H values. And this is just a table you'd be given to do this. You'd be given the heat of formations if you were expected to calculate enthalpy of reaction using heat of formation. So let's go ahead and plug those in. And when you multiply that out, you get negative 113, or when you add that together, you get negative 113.06 kJ per mole. Okay, so the third and final way that we can find enthalpy of a reaction is probably the strangest, or maybe just the least intuitive, and it's by a method called Hess's law. So we already know that we can add and subtract reactions. So I have 2 reactions here, and I can go ahead and cancel the carbon dioxides because those are on the product and the reactant side. And then I can cancel half of this oxygen to get 1/2 O2. And then when I add those all together, I end up with this reaction. But even though we know we can do this, what we're looking for right now is enthalpy of reaction. So what does the fact that we can add and subtract reactions tell us about these given heats of reaction? And how can we use them to find the heat of reaction of this sum? So it turns out that Hess's law tells us that the delta H of the overall reaction equals the sum of the delta H's for each step. So for this one, since we didn't do any manipulation to the equations themselves, then our delta H would be equal to 393.5 plus negative 283 kilojoules. But this reaction, this sum of the reactions is a little unusual, and usually we'd have to do a little bit more manipulation than that because they don't turn out so pretty. So here are the rules for adding and manipulating chemical equations to get a third or another target equation. So first, if you multiply an equation by a constant C, you must then multiply delta H by C. And this should make sense because if I multiply an equation by 2 to get coefficients twice that of the original equation, then I have to multiply the heat of formation by 2. And then second, if you flip an equation, you must multiply the equation by -1. And this might seem a little bit confusing at first, but it should make sense given that the delta H of the forward reaction is equal to the negative delta H of the reverse reaction. So if I'm flipping an equation, I'm just getting the reverse reaction of the original, so I have to multiply that delta H by -1. So here's a pretty basic example of using Hess's law to find the heat of reaction of the target equation. So I have 3 equations that I need to find a way to add together in order to get this target equation. So let's see what sorts of changes I need to make. So the first one that I see is that we need this CS2 to become a reactant. So I can decide that I need to flip this equation. And then I also noticed that I don't have any sulfur in my target equation, but I have it in two places up in the reactions that I'm adding together. So if I know that I'm going to flip this third equation, then I know that when I flip it, the 2s on this one is going to become a product. So I can leave the sulfur over here to be a reactant so that they'll cancel, but I do need to multiply it by 2, so it's enough to cancel the sulfur completely. So let's go ahead and see if those are enough changes to get our target equation. So here I have the three equations that we're adding together, but I made the changes that we said we were going to make. And I multiplied this one by 2, and I multiplied this one, and I flipped this one. And so before I start adding together the reactions, I want to first point out that these delta H values have changed from what they were before. So because I multiplied this equation by 2, I had to multiply the delta H value by 2. And because I flipped this equation, I had to multiply the delta H by -1. So let's go ahead and see if these changes worked out to give us our target equation. So we're going to go ahead and cancel the sulfur, and we can also cancel the carbons. And that leaves us with 3 oxygens, CO2, 2 SO2, and CS2. So we see that that does indeed give us our target equation. But what we were looking for was the delta H of this target equation. And so in order to find that, we just sum, according to Hess's law, we sum the delta H's of the individual steps that we use to get here. So when we add together all of these values here, we're going to end up with negative 1,075 kilojoules per mole. And that is how to find the heat of reaction using Hess's law and summing equations. So I wanted to wrap up with a quick summary of everything we've covered today and a summary of the AP Chemistry thermodynamic unit in general. So first, we learned that changes in heat and work cause a change in the energy of a system. Second, we learned that the sum of the energy of a system plus the energy of the surroundings is constant according to the first law of thermodynamics, and that this fact allows us to simplify calorimetry equations. Third, we learned that the molar enthalpy of phase change and the enthalpy of reaction, when given, help us to find the value of Q for a given quantity of a process or a reaction. Lastly, we learned that if we aren't given the heat of reaction, we can find it using bond enthalpy, heat of formation, or Hess's law. So that is a really quick overview of everything we learned today, and I really hope that this video helped. Thanks!